All right, thank you all. Thanks for being here. It is indeed my first time at Cosyne, and I am not a neuroscientist by training. I'm a computer scientist by training, so I'll be giving maybe an unconventional talk on, sort of my take on some of the modeling approaches being used at this that I've seen at this conference, and sort of connecting to some of the other topics that I've been exposed to, and hopefully you find this informative for your research as well. So I did a lot of work, and I continue to do a lot of work in behavior tracking data. And taking a step back from neuroscience, this comes across in many different forms, from purely virtual. This is a screenshot from World of Warcraft, where you can collect literally billions of frames of behavior data of people interacting in virtual worlds, completely perfectly tracked because it's in a virtual environment with people behaving in it. During my time at Disney Research, we worked on audience analysis, where we tracked the body postures and facial expressions of people as they watch movies. Obviously, lots of applications in neuroscience and ethology, sports analytics, behavior of physical systems. So here the behavior is not some higher cognitive output, but just fundamental physics, and then things like facial expressions as well. So really a wide variety. And what are some things you can do in behavior modeling given this broad context? Well, you can do things like cataloging and detection. This is typically handled as a supervised learning problem. You can do things like content generation, typically handled as a generative modeling problem. And then, of course, there are things that, like discovery, things that are near and dear to many people here, typically handled as an unsupervised learning problem. And I'm just going to give a couple of examples of some of the applications that were moderately successful in other domains. And hopefully the audio works here. I'm just going to stick this to the thing. This is an application with collaboration with Disney Research in data-driven lip syncing in almost real time.
Deutsche Wörter sind sehr viel länger als englische Wörter. Mal sehen, ob das trotzdem funktioniert.
한 가지 언어는 충분하지 못해.
Jeśli kiedykolwiek będziesz odwiedzał Polskę, polecam Kraków.
මම දල්දා මාලිගාව වැඳීමට සෙනසුරාදා හවස ගියමි.
你们真讨厌，吃饱了喝足了就坐那儿看我说话。
Okay. Usually the audience is more Chinese speakers and people laugh more, but that's okay. Here's another application in a concept in sports analytics called ghosting, where you take a replay where your team lost or played badly, and you take a neural net or any machine learning approach, train it on maybe the defensive strategies of a better team, ghost the replay where you show what the defender should have done, and you use this for broad sort of strategic analysis. This is the type of application that arises commonly in sports analytics. But that was behavior modeling, excuse me. Of course, the title of my talk is Interpretable Behavior Modeling. And that begs the question, what does interpretability mean? And this is sort of, I think, a question that many people have debated on and off during this conference. And so here's my definition. It's a pretty generic, almost a meta definition, but I actually do feel very strongly about it. The definition is as follows. Interpretability is basically parsimony under a description language. And so description language is typically expressed or implemented as a modeling framework. Parsimony is essentially a notion of sparsity or simplicity. And this can arise in many different contexts. You pick your modeling framework. So here we have everything from linear models all the way up to neural networks. And then within each modeling framework, you can specify a way of measuring parsimony. Things like few non-zeros, which is the traditional notion of sparsity. Low dimensions, in decision trees, few nodes. In spatial models, smoothness or few modes. Symbolic regression, few components. Neural networks, who knows? Actually, a side note, my group has a separate project on what's called neurosymbolic learning, which perhaps could be a partial answer to this in the future. If you're interested, you can check out our website, neurosymbolic.org. It's a broad collaboration across multiple schools. And there's also other things I should mention, not just parsimony and description language. Are you doing static analysis versus per instance analysis? Static analysis is just the entire model as is. Per instance is how the model behaves when given an input and as you trace its output. Global versus local, looking at just this part of the model or the whole model. But this is my definition of interpretability. The reason why I define it this way is because it gives us a framework or a rubric to make the definitional process of what is interpretability more tractable depending on the application. in my opinion, many of the disagreements about what interpretability is arises from not clearly defining one or more of these two components. And so we have to define these clearly in the context of the use case, and then we have a working definition of interpretability for the application at hand. So how are we going to use interpretable models? In my group, we work on both decision-making or autonomy, where interpretable models can be used in things like medical advice, autonomy. I currently am on sabbatical at a self-driving car company, and things like social recommender systems within social and financial contexts. In scientific analysis, you have things like pattern finding and experiment design. And the example on the right, we're trying to do epidural electrostimulation for people suffering from paraplegia. And the usage patterns are actually quite broad across both of these usage cases. On the left-hand side, you want things like explainable decisions. Why did the medical assistant make this recommendation? What is a very concise description of that? Why should we trust this recommendation? If there was an unexpected outcome, let's say the self-driving car got stuck somewhere, can the engineer debug this whole stack to find out what was causing the problem? Furthermore, when we choose to spend lots of time and resources to design an experiment, we should be able to justify that investment. And so that should also be an explainable decision. So the usage pattern is actually quite broad. And so here's an example from a clinical practice from, this is not my work, this is work by Burke Ustin and Cynthia Rudin. Burke was a student of Cynthia's, and he's now a new assistant professor at UC San Diego. His work is great. This is what's called a risk score, which is used in clinical medical decision making. It's actually pretty simple, right? You have a number of questions, and each positive answer to these questions gives you a point, and if the points sum up to a high enough number, it's a problem. And then there's sort of a recourse. And in this particular context, what does parsimony mean? Parsimony means there are few variables, not that many. Parsimony also means that the values, the thresholds, and the points are all integers. They're not real value. And in fact, in their paper, they compared against an alternative version using normal least squares regression, where they have like lots of features, and the points are like 0.723, 1.4, and you can easily see that a doctor would never agree to use that. Of course, parsimony is also relative. This is a decision tree. It's a real-world decision tree. I argue that it is not interpretable, right? It's because it is not parsimonious. Or at least for me, maybe to an expert it is. And as an aside, this is all related to, of course, to the concept of Occam's razor. I won't read the whole quote, it's from Wikipedia, but I'll just simply highlight the idea that the Occam's razor is itself an instantiation of the principle of parsimony. So I think of interpretability as hand in hand with Occam's razor, just in perhaps a more expanded scope. If you're interested in learning more about interpretability as it arises in machine learning, including deep neural networks, there are many references available now, tutorials, keynote talks. This one you see on the top left is quite nice. It's a keynote from iClear last year by my colleague Bean Kim, who is a research scientist at Google Brain. And it's a really nice and accessible talk about interpretability, and there are a range of other tutorials as well. I will share my slides, so if you don't catch this right away, you can click on the links afterwards. OK, so for the rest of this talk, I want to dig a little bit into one family of models, one that is very often used by this community. I also recognize that many of you are coming from a quite diverse background. Some of you have less computational backgrounds than others. Some of you might just be getting into machine learning for the first time. So I'm trying to make this as accessible as possible. So I'm going to cover, just in a few minutes, the basics of latent variable models in what I hope to be a unified way. And parsimony here arises principally through the concept of low rank. So there are very few dimensions in this latent variable model. In some applications, we'll also want models that are smooth. And so hopefully this gives you a somewhat unified perspective. And primarily I'll be approaching this from an optimization perspective. And then I'll sort of, as we go along, walk through a few applications that my group has worked on in the context of behavior analysis. So here's the basic setup. We have an observed variable. I'll call it x. It lives in a d-dimensional space. We have an encoder that's in red, parameters by phi, and then we have a latent variable associated with this observed variable. I'll call it z, and it's the output of applying the encoder to x. And it lives in a k-dimensional space. Typically, k is much lower dimensional than d. So the goal is to learn a good encoder f from training data. And good is typically expressed or quantified using a loss function. And in this talk, I will mostly be restricted to good in the context of reconstruction. So what that means is now we also add a decoder from z to x prime, where x prime is a reconstruction of x. And now we can express this as a loss function. The loss function is written as follows, where we have a loss on, you apply the encoder f to x, you apply the decoder g onto the encoding, and you compute the loss. We also have what I typically call some sort of well-conditioning of the latent space. That's the second loss. And so in summary, you want to learn an encoder-decoder, also known as an autoencoder, that reconstructs the data and has a well-conditioned latent space. This is sort of the high-level basic setup. A few comments. Most people, when they first start, they implement the loss using squared loss, which is functionally equivalent to Gaussian log likelihood if you have a probabilistic model. If you do things like the singular value decomposition or principal component analysis, then f is typically linear with no nonlinearities. And in fact, g is just the pseudo-inverse of f. In other words, f is a d by k matrix. And so you may have seen this in your sort of data analysis class, where if x is represented as a data matrix, every column is a data point, then it's approximately equal to this factorization. And here I color-coded everything, so you see the correspondences exactly. Every column of z is one of your latent codes, and f is just a linear encoder, and it's also the decoder in this special case. And so what I'm basically showing you here is, on the one hand, an autoencoding viewpoint framed as an optimization problem. On the other hand, a matrix factorization viewpoint framed using basic linear algebra, and they're mathematically equivalent to each other, and you can sort of at least conceptually swap between them as it's convenient for your modeling needs. And I know that not everyone here has actually coded in PyTorch before, so I just want to show you that it is super easy these days to build your own network suited to your needs. You don't have to download someone else's code, run it, and pray that it works. You can build it yourself as you need it, tailored to your needs. And so here's an encoder. This is PyTorch. The thing I want you to notice here, and this is just a few lines of code. This is a linear encoder, and so what you see there is basically a linear encoder, d by k matrix. That's literally what it says. And then when you run the forward inference step, you just apply that matrix to your input. That's all it says. Similarly, the decoder is a linear decoder, same thing, except for d by k, it's k by d. That's what that line says. And then the autoencoder just instantiates the encoder and the decoder, and then it returns, and in this case, it returns both the reconstruction and the latent variable. So it's really just, the important lines of code is just like 5 lines of code. It literally looks like pseudocode. OK, suppose we want a nonlinear encoder. Now that we've written essentially the singular value decomposition in PyTorch. Now let's say, OK, we want a nonlinear encoder. Well, all I've done here is instead of having one layer, I have 2 layers, right? First, I go from D to H, where H is the size of the hidden unit of the 2-layer neural network. Then the second layer goes from H to K. And then when I do forward inference, I have this ReLU in the middle because it's a nonlinearity. And that's it. This just with a 2-line change, I've changed my linear encoder to a 2-layer nonlinear encoder. That's it. Same thing with the decoder. And then the autoencoder class is completely unchanged. Don't even need to change it. It's abstracted away. That's it. OK, so that was just to show you that getting started and building your own encoder-decoder framework is actually quite simple. Yes, question?
Sorry, can you tell us what the second L is? You said L is squared loss, but it looked like you have 2 L's in your equation.
OK, so the question.
You said it was going to be for regularization.
Yes, so the question is, what is the second L? For singular value decomposition, that second L has to be squared loss as well. And you can see that and it's equivalent to the fact that in the singular value decomposition, this is the minimum variance matrix factorization that captures as much of the primary variance as possible, which we can derive offline if you'd like. But what that means as an optimization problem is that you need a squared loss on Z. There was a murmur about a rank constraint. I'm happy to talk offline about when and where this is equivalent. I'm fudging a little bit. It's not equivalent all the time. It's equivalent sometimes. It's equivalent in the most useful times, but I'm happy to talk offline. Okay, so a few comments. Now that I just showed you how easy it is to get started, it is straightforward to extend to nonlinear. I just showed you an example. You can regularize in various other ways. You can regularize Z to be sparse rather than so that it has few non-zero entries rather than be sort of, have a small volume as measured by the ball. Or F can also have a smoothness metric. You can use other learning signals beyond autoencoding. You can use self-supervised learning. You can use contrastive learning, etc. You can add more structure in various ways. You can make this be more probabilistic. You could have a hierarchical structure. You can encode different types of latent content. And I'll go through for examples. Here's one of my favorite ones. This is an application in fine-grained spatial modeling of basketball gameplay. So here, the data set is as follows. We have tracking data from the 2012-2013 NBA season. For the purposes of this model, we've discretized the half court into 1 foot by 1 foot cells. So there's about 2,000 cells here. And what you're seeing here is the propensity map of the shooting profile of one of the best NBA players to play during that era, Tim Duncan. And the idea is to learn generalizable patterns of shooting propensity across players. Okay, so let me just pull everything up. And so what we're going to do, I'm going to take the matrix factorization viewpoint here because it's more convenient, although we actually implemented it in using the optimization paradigm. So we flattened the half court into a vector. So every column is the shooting propensity of a player. It's actually more complicated than that. We have multiple data points, but let's ignore that for now. And then capital N is the number of players. It was 435 during the 2012-2013 season. And then that basically is factorized into this F and a Z, or Z. Each column of Z is the latent code representing the behavior of every player. And so we can visualize F, so K equals 10 here. And these are just the visualizations of every player. And, of every latent factor. And you can see it basically corresponds to shooting archetypes. So this model has automatically discovered from looking at shooting profiles of NBA players that there are players who like to shoot from the corner 3, players that like to shoot from the wing 3, top of the key, left wing, right wing, free throw area, etc. And then if you then apply this to the latent code and do this inner product, you can get this reconstruction of the shooting profile of every player in the NBA. And from this, you can just compare players by comparing their latent codes. And by the way, this was the last time that I was ever a first author on a paper. So this paper is near and dear to my heart. Okay, so that's one example. Many of you have worked with variation autoencoders. Some of you might be wondering, okay, how do we actually go from there, what we just saw, to variation autoencoders in as conceptually as easy way as possible? Okay, given everything that I just described, one can, at least at a high level, explain variational autoencoders very simply. Instead of estimating a single Z in the encoder, my goal is now to estimate a distribution over Z. So in particular, the most common applications encode a Gaussian. So the encoder now encodes maps to a mean and a standard deviation. That's the main difference between what you just saw with the singular value decomposition and nonlinear autoencoders and a variational autoencoder. And then, of course, when you want to do a reconstruction, now you have to actually draw a sample. You have to draw a sample from this Gaussian, and then you do the reconstruction. That's the basic idea. The loss function has the exact same macro form. The loss on the reconstruction because you have to sample a Z, it's over the expectation over samples of Z. And the right-hand side is a regularization that we want to regularize Z to be close to the white Gaussian, to the uninformed Gaussian. And these are implemented using KL divergence type terms. But ignoring things like KL divergence, the implementation details at a macro level, this is what's happening. It has the exact same functional form as everything I just described before. Okay, So given all of these things as building blocks, we can start to assemble them in ways that suits our needs. So here's another application that I worked on with the Walt Disney Company. And here we're doing audience analysis. So you collect data of facial expressions of people watching movies, and then you can extract face landmarks. That's your observed variable X. And now you can apply this into a latent space. And now we're doing two things in a hierarchical fashion. We have a nonlinear encoder that takes you to a Z, and then we actually break that Z further into a factorized U and V. And it's factorized using two pieces of metadata. Number one, you have the timestamp of the movie, and number two, you have the ID of the audience. So the audience is anonymized, but you have the audience ID. So for any point in time, I know the facial expression of audience member 3. And so now I have 2 rounds of dimensionality reduction, basically. And then you could do the reconstruction. By the way, this is the first author is Zhiwei Deng, who was a intern at Disney Research when he did this work. He's now a postdoc at Princeton. And now you can actually visualize some of the latent factors. Here I'm just visualizing the latent factor for one of the points in time. And you could see that one of the dimensions correspond to kind of a neutral. The 0 is neutral, and you can have like smiling versus laughing, or at least mouth wide open. And if you're an analyst in the media companies, you can sort of use this latent space, which is very low dimensional, to look at common pockets where where groups of audience members reacted the same way. Like this subpopulation laughed at time step 3 minutes and at time step 7 minutes simultaneously. Now you can use that to quickly zero in your investigative resources to figure out what those things have in common. Is that good or bad for the movie? Should I sort of change the movie up or something like that? Okay, the last thing that I'll just describe real quick is a new project on key point discovery. So this is more related to behavioral neuroscience. So one thing that is challenging as we move to sort of more diverse types of behaviors in diverse organisms is the fact that labeling the key points, like the nose or the tail of the animals, et cetera, requires a lot of supervised labels, especially for non-traditional animals. What you see here are automatically discovered key points, and the key points are actually themselves part of the latent representation from using in a completely unsupervised way. The power of this approach, of course, is not in having better key points for mice. It's in having better key points from completely novel viewpoints, completely novel model organisms, things that are not even animals, like trees, and trying to go as fine-grained as possible. And this works out of the box. You just give us your movie, we give you key points. So you can try it yourself by clicking that link and filling out the form. This work was led by my student Jennifer Sun, who is currently on the faculty market. So the basic idea is as follows. In the context of this talk, the main thing I'm going to focus on is the fact that it is a structured latent space. In particular, this architecture, which I know it looks complicated, but it's actually it makes a lot of sense if you build it incrementally in the way I'm trying to preach. But the main thing in the context of this talk is that it has two notions of a latent space. It has a pose and appearance. And the pose is the key points, and the appearance of the other stuff, right? And so this decoder basically can decode separately pose, or at least in the middle layer, separately pose and key points, and then pose and appearance, and then we of course throw away the appearance for the actual downstream application, but it's there to capture the variance of things like appearance. There are other things that we did that I don't want to get into. The main thing I want to emphasize is that this is essentially a structured prior. Our latent space should capture both geometry and appearance, and we will only care about the geometry, and we can just extract that at the end of the day. Okay, so I'll wrap up right on time. Closing thoughts. My definition of interpretability is parsimony under description language. It is important to define both of these for your application. If you only define one, you'll be talking past each other. And there are many tutorials and resources out there if you want to get started on learning more about this. The key building blocks are very simple these days, especially with modern deep learning tools. They're very easy to use. I can barely program anymore, and I was able to make sense of the PyTorch example. And understanding how these computational methods and concepts are connected to each other in this unified way will empower you to create tools that suit your needs. I think I misspelled suit, but that's okay. Thank you for your attention.